Hi, James again. In this problem, a changing magnetic field produces an EMF. There's no wire loop, but there's an EMF, so there's an electric field, and we're going to find the electric field using the relation between electric field and EMF, the integral E dot ds equals EMF relation. So to start, we use Faraday's law to find the EMF at point P2, which is the first thing we're finding. And so Faraday's law, I'm just going to take the absolute value. I'm just going to take the magnitude of the EMF because I'm interested in the magnitude of the electric field. I'm not. I would not look for direction in this way, using the expression for Faraday's law anyway. I wouldn't use the minus sign to look for any sort of direction. So I'm just going to take the magnitude, which is this, and there's only one loop. I mean, if I put a loop in here, there would just be one of them. And in fact, what I'm going to do eventually is I'm going to relate the EMF to the integral around a loop of the E field dot a bit of arc length on the loop. So let me put in a loop just to show what I'm going to be talking about there. And the symmetry of this problem is cylindrical, or the symmetry of a circle in this plane in which the problem is illustrated. It might be a little bit deceptive that the grid of x's indicating the direction of the magnetic field does not have circular symmetry, but it's meant to represent a uniform field in a circle, so it is meant to illustrate cylindrical symmetry, or the symmetry of the circle. So I can do this integral most simply by drawing a loop that's a circle centered at the center of the region with non-zero B field, and so I've got a circle of radius R2. So that's, I can think of that as my loop. So anyway, n is 1 is the point of that. And d phi b dt is d dt, as usual, of the B field times the area times cosine of the angle between them. The area isn't changing because my R2 isn't changing. And the angle isn't changing. It's, in fact, the angle is just 0 degrees, as is often the case, because the angle is between the area vector, which is normal to the plane of the loop, and the B field, which is also normal to the plane of the loop because it's into the page. That's what the x's mean. So the angle is just 0. Both B and A vectors are into the page. So that's 1 times d dt of A, which doesn't change. It's just the circle of area of the circle with radius R2. Cosine theta, which doesn't change. It's just 0 degrees. So I can take A cosine theta out of the derivative and say it's A cosine 0 degrees, and then dB dt. And cosine 0 degrees is just 1. So I wind up with A dB dt, where in this case A is pi R2 squared, because that's the area of this loop. So pi R2 squared dB dt is the EMF. Now, to get the E field, I say that the EMF is this integral around a closed loop of E dot ds. Closed loop, I'm going to use the circle because that has the symmetry of the problem. Because the problem has cylindrical symmetry, the symmetry of the circle here, the E field can't vary on the loop. It can't vary as you rotate the page or the situation, because the situation doesn't change as you rotate it. And so the E field can't change as you go around this circle, because the circle has the same symmetry as everything else in the problem. In addition, the E field is tangent to the circle. The reason for that comes from Maxwell's equations, and I'll just leave it at that. The E field is going to be tangent to the circle, as is the bit of arc length. So the E field is going to be, I'd have to do my right-hand rule to decide whether the E field is that way or that way. But in any case, it's going to be tangent to the circle, as is the bit of arc length. So because of that, they're parallel to each other. So I get E ds cosine theta because they're parallel to each other. That's just the dot product. Because they're parallel to each other, it's E ds cosine 0 degrees again. Because E is constant as I integrate around the loop, I bring it out of the integral. Cosine 0 degrees is just 1, so it's the integral of ds. Integral of ds is the arc length, total arc length for the loop. So arc length for the circle is the circumference of the circle, so 2 pi times the radius of the circle, which is r2. And so the EMF is, I'm sorry, the E field, rather, is the EMF divided by 2 pi r2. And I'm not interested in direction here, so I'm just going to take, I mean, the E field is the magnitude, so I really should take the absolute value. Good. So I calculate the E field, which is the EMF over 2 pi r2. This is the EMF, so I plug this in for EMF. It's pi r2 squared dB dt, and divide that by 2 pi r2. And so I wind up with, my pi's are going to cancel, one factor of r2 cancels, so I get r2 over 2 dB dt. So r2 over 2 ddt of b, which is, I have it up here, it's 0.071 t squared plus 1.4. And if I take the derivative of the constant, that just goes away. The derivative of t squared is 2t, so I get r2 over 2, 0.071, oh yeah, times 0.071 times 2t. And if I plug in numbers, I look at the problem again. R2 is 0.02 meters, so I get 0.02 meters over 2 times 0.071 times 2 times the time, which is 2.2 seconds. And I will, well, I get 2 divided by 2. That goes away. So 2 times 0.02 is 0.04. 0.044 times 0.07. I might as well put it into a calculator. It's silly. And yes, you get 0.0031 volts per meter. Volts per meter because it's an electric field. And if you notice that this is a little cramped here, it's because I wrote down volts. I've been doing Faraday's law problems, and I forgot I was calculating an E field. So yeah, it's volts per meter because this is an E field. And that's your answer. Now, there is a second problem we can do. This is now the end of the problem that's actually in the homework. But there's a second problem we can do from the given information. So I'll do it just for the heck of it. And it's this. It's what's the E field at, magnitude of the E field at P1. So B would be E at P1. And we already have most of our work done. We found that the E field was the EMF divided by the circumference of the circle that goes through the point where we're finding the magnitude of the E field. So it's magnitude of the EMF divided by 2 pi times the radius of the circle we're talking about. So I'll just put radius of the circle. Okay. And the EMF was this pi r2 squared. So it's the area of another circle times dB dt. So this is, I'll put area of the circle with where the flux is. Times dB dt. So remember, we got the EMF, this thing from looking at the flux through a circular region, and that the change in the flux through a circular region, the rate of change of flux. And that rate of change was the area, because it wasn't changing, times the rate of change of the B field, because the flux is an area times a B field times cosine. I'm sorry, is the ddt of an area times a B field times cosine of the angle between the area vector and the B field vector. So yeah, it's the area of the circle with the flux times dB dt in this problem is the EMF, and then the electric field magnitude is that divided by 2 pi times radius of the circle through the point that we're talking about. So circle through, in this case, P1. And what you can do if you want to verify that is just go through the same steps we did to get the answer to part A, but do it for P1. And here's the circle that goes through P1, right? Just as we had the circle that went through P2 was this. And the radius of that circle is R1. And the region with the flux, it has a radius of big R. It's this region here. So the difference in this part B is that the region with the region that's bounded by the circle through P1 includes a portion of itself where there is no B field and hence no flux. So the place with the flux is smaller than this full circle. That was not the case when we had the smaller circle that was completely contained in the region with the B field. So anyway, the E field magnitude then is the area of the circle with the flux, which is pi times big R squared, times dB dt, divided by 2 pi times the radius of the circle through P1. Well, that radius is R1. This is the circle through P1. That's its radius. So 2 pi R1. And so the pi's cancel. We have a bit more to plug in this time. R squared. dB dt, again, B is the 0.071 t squared plus 1.4. So actually, I'll just write R squared over 2R1 ddt of B, which is the 0.071 t squared plus 1.4. And so you get R squared over 2R1. ddt, again, of this, ddt of t squared is 2 times that. Sorry, ddt of t squared is 2t, and then multiplied by that. So 2t, 0.071. And ddt of the 1.4 is just 0. So rather than flipping to another page, I'll just continue on this line. Please excuse the poor style. And so R is 2.5 centimeters. So R squared is 0.025 meters squared divided by 2 times R1. R1 is the R1 is not given. So So I'm going to leave this in terms of R1. Yeah, so magnetic field and R1 is not given because, yeah, we don't have that part of the problem. So I'll just leave it in terms of R1. So 2R1 times 2t. T is the 2.2 seconds times 0.071. And so you wind up with, I'll pause and just calculate all that. So you get 9.8 times 10 to the negative 5 divided by R1 units. And it's an E field. Be a fun thing, maybe pause and ask yourself what the units of this are before I reveal them. All right, so the units of an E field are volts per meter or newtons per coulomb. Either way, I'll go with volts per meter. This expression, though, has R1 downstairs. R1 is a variable for a length, a radius. It has meters in it. So volts per meter are the overall units of the E field. But because I've got meters downstairs here, the units I write out here are just volts, because now this whole thing will have units of volts divided by meters, because R1, it has a number inside it and a unit of meters. Okay. And so that is the answer. So yeah, this is not the EMF, because remember we took the EMF and we divided by 2 pi in addition to dividing by the R1, but it is dimensionally a voltage. So, hopefully I didn't make any mistake there, because I have no answer to compare it to, but that's the idea. The denominator of our E field depends on the circumference of the circle that goes through the point where we're finding the E field. That circle has circumference 2 pi R1, where R1 is this big radius out to P1. And the EMF has the area of a circle with flux in it, with flux through it. And that circle has radius big R, because the larger circle with big radius R1 doesn't contain any B field in part of itself. So the area of the circle with the flux that gives rise to the EMF out here is big R, not R1. So hopefully of interest. But anyway, that's a bonus bit of a problem, and hope that was of use. And thank you for watching, and have a good day.